Okay, so we will continue this problem. We were talking about the velocity and tangential acceleration that is in common between the two gears. Okay, so this is the first point of, if you want, the gear C, that we know velocity and tangential acceleration. The second characteristic point of gear C is the point in contact with gear B. So as you can see here, you have also that the gear C is in contact with gear B. They have a common point. They are in mesh. So at this level, we have also common velocity, linear velocity, and tangential acceleration. So here we can say that if you want, let us call the points. So we have this point, let's say, is E, and this point is F. Okay, so for these 2 points, we can write that velocity of E is vector, VE vector, is equal to minus omega A RA along I, while for point F, which is in contact with gear B, so point F is characterized by a velocity of, now we will take F as a point of the big gear of gear B. This big gear B is doing what? If you imagine, it's doing rotation about fixed axis passing by A. Okay, so this rotation is of radius equal to the following one. I will take the distance from here, from A to F. So the radius will be RA plus R of D plus R of C. I will divide it into 3 parts. This is RA, this is RD, and this is RC. Okay, so I can write that VF is plus omega B times RA plus RD plus RC. Okay, now once I know the characteristic velocity of 2 points of a rigid body, I can relate these velocities in order to find omega of the rigid body. So both points E and F are part of disk C, and disk C and D are welded together, and they form one rigid body. Okay, so here disk C has an inner hub and an outer hub, and they will rotate together at the same angular velocity, and our purpose is to determine what is this angular velocity. Now we have 2 methods here. We can work with the vectorial formulation, and we can work with the instantaneous center method. Both will give you the same result. Let us try both. Okay, so if you want to use the instantaneous center method, you should join the extremity of VE to the extremity of VF. And if you remember, when we did the course analysis, we said that we should find the position of the هلا هون مبينه كأنه دي بس هي it's not the case, so it depends on the value of VF. So let's say vector VF is like this. So it depends on the values. يعني مفروض نرسمهم to scale تنعرف مظبوط وين ال IC. Okay, so let's say VF is until here, for example, and the IC is, let's say, at this level. How to find the position, the actual position of the IC? In order to do this, we can name this distance x. So we say that the distance to IC is x, and then the remaining distance will be the total distance separating EF minus x. And to calculate the value of x, then we can say we will use the Taylor's theorem or the similar triangles concept. So we can write that the velocity of point E over the distance from E to IC, which is x, is equal to the velocity at point F over the distance from IC to F, which is EF, and EF is equal to this number, RA plus RD plus RC. This is EF. Okay, so over EF minus X. Knowing the value of VE, VF, and EF, the only unknown in this equation is X. Once we find X, we can find omega simply by saying that omega of gear C is just equal to the ratio of velocity of E over X, or also we can write it as velocity of F over EF minus X. So both will give us the same value, which is omega C. So this is a first method to find omega of C. Okay. Now, a second method is to use the vectorial relation between points E and F. So let us do it. From the velocity of E and F, we can say that it's clear that omega of C is counterclockwise. So we say that omega of C is counterclockwise, and we can verify this from our calculation. So if we write the relation, the vectorial relation, let us clear in order to write. So the vectorial relation between points E and F will be as follows. We can write that V of F, or V of E if you want, is equal to V of F plus omega of the disk, omega C, vectorial Fe. And now let us replace each term by its expression. For point E, it is along minus I, and it's equal in magnitude to omega A or A. So we replace VE by minus omega A or A along I equals to. For point F, we said it's along plus I, so it's plus omega B times the distance from A to F, which was RA plus RC plus RD along I, and plus, because we said that we will assume omega counterclockwise, so it's plus omega CK vectorial Fe. Now concerning vector Fe, this is vector Fe, it's along positive J, and it's equal in magnitude to RC plus RD. So it's vectorial RC plus RD along J. So now all we have to do is to expand. You have K vectorial J is minus I. Okay, so as you can see here, all your terms are along I. You don't have any term along J. So if you compare along I, what do you get? You get the first term is, from the left side, is minus omega A RA, equals to, from the other side, you have omega B times RA plus RC plus RD, and minus omega C times RC plus RD. This will give you this equation, your first equation. And this, yes.
ليه شو اسمه اول واحده equation when WRA equals WB RA plus RC plus RD. ليه مش بس RD؟
Okay. لأنه here what we did here we calculated which velocity of point F صح؟ Point F is common between gear C and gear B صح؟ شو عم يعمل gear B? Look at the figure. Gear B is rotating about which point? انت تخيلوا للجير B هو إذا بتكمله هو it's a big gear okay and it's rotating about an axis a fixed axis passing by A لأنه إذا بتلاحظ the distance from يعني this is the fixed point for gear B هو عم يبرم around this axis which is equidistant from all of its points okay منه عم يبرم around D لأنه طلع D is not equidistant from all point of your gear هو عم يبرم around this axis بما انه عم يبرم about an axis fixed axis passing by A the radius of rotation تبعه بيكون equal to this whole distance okay يعني انت بس تاخد point F and you want to calculate the velocity of F you should consider omega B times the distance to the fixed axis of rotation of this gear اللي هي decomposed into three parts it is radius of A plus 2 times the radius of D أو إذا بدك RD لهون ومن D لتحت تاخد RC okay RC is the distance from D to here this is why the total distance from A to F will be RA plus RD and plus RC okay
Okay, thank you, doctor.
okay any other question on this okay so now what we did until now, we have calculated omega c, okay? The angular velocity of gear C. But what they asked for the angular acceleration of C, not only the angular velocity. But in order to find the angular acceleration, we need to pass by the angular velocity, okay? Now, what can we do? نحن قلنا كمان إنه here we have several methods or we can relate acceleration of points okay or also we can say this relation is relating at any if you want position I can have this correlation relating the omega A omega B and omega C it's valid at any position this relation this is why I can derive it with respect to time. So if I derive this relation with respect to time, I can get a relation between alpha because the derivative of omega A with respect to time is alpha A. The derivative of omega B is alpha B. And the derivative of omega C is alpha C. So by just deriving this relation with respect to time, I can get a relation between alpha A, alpha B, and alpha C. And since alpha A and alpha B are provided, the only unknown will be alpha C, and I can calculate then what is the angular acceleration of gear C. If I didn't pay attention for this method, what I can do, I can relate the acceleration of 2 points of the disk. But please pay attention, مثل ما قلنا, tangential acceleration is common between two gears in contact, but not the normal one, not normal acceleration. And if you take the same points E and F, okay, if you want to write the acceleration of E, okay, the acceleration of E as a point of gear C will be as follows. Acceleration of E can be decomposed into tangential acceleration and normal acceleration. Now, concerning the tangential acceleration, it is in common with A because the linear velocity is the same. At any instant, the contact point will have the same linear velocity, okay? And therefore, it will have also the same tangential acceleration, okay? So we can say that A tangential of E can be replaced by minus alpha A times RA along I. But for the normal component, okay, the normal component is different. And it's a little bit hard here if you want to find it. You know why? Because in general, the normal component is equal to omega square. In general, we find it as omega square times R. Okay? But R represents what? When we write it like this, AT plus AN, this means that we know the center of curvature. Okay, but here we don't know the center of curvature at this instant. We don't know E is rotating about what, because we have a general motion for disk C. Okay, so concerning point E, we cannot already know what is the two components of its acceleration. Here we can keep it as, but what we are sure of is that the normal acceleration is along J. This is what we are sure of. But what is the magnitude, the exact magnitude of AN, we don't know. Okay, so what you can do here, you can just replace it by A and E along J, because as you will see here, what will simplify the analysis for you is that all normal accelerations are along J. So you don't need to know that. You just need to know the components along I, because the tangential accelerations here are along I and the normal accelerations are along J. So even if you don't know the value of the normal acceleration, it's not a problem for you, because when you compare along I, you will not have any term for AN, because AN is along J. Okay, so all you have to do then is to write AE and AF and keep AN as an unknown. Okay, and when you compare along I, you will get just this relation. You will go back to this relation, this one, sorry, again, which relates alpha. And the first term, for example, you get it from AE, which is minus alpha ARA, and this the other terms you will this one alpha BRA plus RD plus RC, you will get it from the tangential acceleration of point F. While this term, you will get it from when you do alpha vectorial FE. You will get this term. Okay. So by comparing along I, you will get this relation again, irrespective of the values of normal acceleration at E and normal acceleration at F. Now, how you can find these components, A and E, A and F, you can find them after calculating alpha. Because once you calculate alpha of your disk C, then you can find the acceleration of any point of your disk by just applying the rule. And you just relate E and F again. So your unknowns will be AN, E, and A and F. You can get. Okay. Now, in particular here, they asked you for the acceleration of the center point D. We want to calculate what is the acceleration of D. In order to calculate the acceleration of D, we will use first, we have calculated alpha C and omega C, we know that. So now we know the value of omega C and alpha C. And the question is how to find now what is the acceleration of point D. We should pay attention for something, that here D always in any problem, when you have a disk, the easiest point to get information about acceleration is the center of the disk, because the center of the disk, you can draw its path easily. For example, here, point D is doing what? Point D is moving along a circle. In general, نحن معودين إنه it moves along a straight line. لأنه بتكون the ground is a straight line and the distance from the center to the straight line is fixed. So C will move along a straight line. Here it's different because this is in mesh with a gear. Okay, so here this distance is constant, but because this line has a circular form, then D will move along a circle. Okay, it's moving along a circle, and a circle of radius of center A and radius RA plus RD. So this is the path of motion of the center. So the center is moving along is doing rotation about a fixed axis. So in this case, how we can write the expression of its acceleration? We can say that the acceleration of point D is decomposed into two components: tangential acceleration, AT of point D, plus a normal component, AN of point D. Okay. Now, concerning the tangential acceleration of D, we can easily calculate it. Okay. Why? Because here you can find the acceleration of D along I by just relating the accelerations. And you have already what is the acceleration of E, and you have what is the acceleration of F. Okay, so and you have already their velocities, you know VE and you know VF. Okay, so you can find what is the velocity of point D and what is the acceleration of point. Okay, because look, whenever I know the velocities of 2 points, I can get the velocity of any point on my rigid body. Here we already calculated together what is the value of VE, what is the value of VF. So I can find the value of VD, and this will help me into what? Because why I need to find VD? Because you know that the normal acceleration of D, okay, the normal acceleration of D can be written as what? So it's VD square over the radius of curvature of the path of D. And since you know that D is moving on a circle of center A, then you can say that the radius of curvature of motion of D is simply the distance between A and D. So it's AD. Okay? AD is just equal to RA plus RD. So by calculating the velocity of D, you can find what is the normal acceleration of D. So here we can write that it's equal to AD is equal to RA plus RD. And to know the value of the velocity at D, it's very simple. VD, I can get it or from vectorial relation. So I can relate VD or to point E or to point F. So if you write a vectorial relation between VD and VE or VD and VF, you can find the value of VD. Another approach is to use the instantaneous center. So if you remember in the course material, we have already seen an example that how to find. Here we did it together. We found omega and we found x. So now from geometry, you can find the distance between D and the IC. And then by multiplying omega c by this distance, you can get VD by another method. So you can get VD or vectorially or from the instantaneous center method. And once you get it, you say simply that A, the normal acceleration of D, is VD square over rho. Now concerning the tangential acceleration of D, the tangential acceleration of D, you can just find it by relating AD to AE or AD to AF and comparing along I. Because when you compare along I, the tangential acceleration of D will be obtained because you already know the acceleration of E along I, and you'd already know alpha of C. So just by applying the vectorial relation between the two, you get the tangential component. And
دكتور
therefore, yes,
مش احنا اذا بنعمل ريليت لل AD لل AA انه ال AA هي
ما
0 فبيطلع
no,
لنا less variables.
okay, look, if you want to relate to A, okay, if you you need to know what is omega of rotation of D about A. Do you know it? ما بتعرفها. Please
Oh no.
انتبه، اوعى تستعمل الأوميجا C. It's wrong. إذا بدك تعمل relation to A, you need to know what is omega D about A and what is alpha of D about A. وهولي ما بتعرفهم، هلا صار فيك تجيبهم. اوكي؟ من بعد ما انت عملت analysis وعرفت قد ايه tangential acceleration، صار فيك تقول انه alpha about A هي tangential acceleration over RA plus RD. يعني don't confuse you have several types of motion here. اتفقنا؟ يعني نحن اللي جبناهم سوا هن الالفا سي والالفا والاوميجا سي، هول represent الموشن الانجلر موشن اوف ديسك سي اللي هي جنرال موشن. ما فينا استعملهم هول الفاليوز تحلل between D and A what is happening. D is rotating about A مظبوط، بس انا ولا بعرف what is omega of rotation تبعه ولا بعرف alpha of rotation تبعه. هلا صار فيني جيبهم لانه من بعد ما عملت calculation للtangential acceleration of D، اوكي، فيني اقول انه هيدي التانجنشال acceleration فيني اشوفها بطريقتين. فيني اشوفها انه D is a point of gear C، بس فيني اشوفها كمان انه D is rotating about A. And once I know this tangential acceleration I can say انه ساعتها الالفا about A هي هيدي ال AT divided by RA plus RD. اوكي، وصار فيك تجيب الاوميجا بتقول كمان انه VD هي اوميجا of D about A كمان times RA plus RD. اوكي، صار فيك ساعتها تجيب what is the angular motion of D about it. اوكي، clear?
Okay, thank you, doctor.
Any other question? This is a very important problem. بيساعدكم تشوفوا انه how can I see يعني how can I use different values of alpha and omega for points. يعني إذا برجع بتطلع هون على طول كل point فيكم تطلعوا فيه لحاله، فيكم تطلعوا فيه كبارت اوف body. يعني أنا إذا بتطلع بدي لحال، دي لحال عم يعمل rotation about A. بس إذا باخد حيلا point تاني من الديسك C it's doing a different motion. مشان هيك بقول إنه هيدا الجير C is doing a general motion. أوكي؟ بس البوينت في بوينت منه يكون عم يعمل rotation about fixed axis. إذا بتتذكروا نحن وقت ناخذ rigid body in general motion في بوينت منه يكون عم يعمل translation while point تاني يكون عم يعمل rotation. اوكي، ساعتها I can characterize each point بالموشن تبعه، وكمان I can characterize it as the point of the rigid body. اوكي، another problem. Rod AB rotates counterclockwise with constant angular velocity omega. Determine the velocity and acceleration of point C located on the double collar when it is at the position shown. The collar consists of two pin-connected slider blocks which are constrained to move along the circular path and the rod AB. So in the following problem, how should I think? What should I do? If I look at my collar is able of doing what? I can see it in two ways. I can see its motion relative to rod AB. Okay? And if I am on rod AB, إذا بوقف على rod AB, which is rotating, I can see that the collar is doing translation. Okay? But if I am outside of the rod, if I am at a fixed point here, and I look at my collar, I will see that it is doing a circle. It's rotating along this circle, which is a rotation about this fixed axis here. So here I have two types of motion. I have a relative motion. In the frame of the rod, it's translating. In the absolute frame, it's rotating about a fixed axis. بس احكي عن relative motion دغري فكروا بالformulas of rotating axis directly. Okay? What is my purpose here? My purpose is to determine the velocity and the acceleration of C. Okay? When it is at this position. Now, what is the information that I know? I know the motion of the rod. Omega of rod is given, and it's a constant. Because I said that AB is rotating at a constant angular velocity omega. Since omega is constant, then I can say that alpha is 0. So alpha of rod is equal to 0. And my purpose is to determine what is the velocity of and acceleration of C, which has a freedom of motion on my rod. It can translate on it. So since it has a relative motion with respect to the rod, what I will do, as we said, we will use the rotating axis formulation to relate velocity of C to velocity of A and acceleration of C to acceleration of A. So first, in a rotating frame, what is the relation? The general relation is V of C as a vector is equal to V relative, the relative velocity of color C with respect to the rod, plus omega of the rod vectorial AC, and of course plus VA. Okay, but here, because A is fixed, then VA is 0. Okay, so here I am relating the velocities of A and C using the rotating axis formulation. Now A is fixed, so VA is 0. Now I will try to write my other terms. I will start with VC. This component represents the absolute, this is the absolute velocity of C. Okay, so it means it represents the velocity of C that I can't see from a frame that is fixed. So if I am at this point and I look at C, I will see what? I will see that point C is doing rotation about on this circle. Okay, and you know that in rotation, more in case of rotation about a fixed axis, the velocity of point C will be perpendicular to the radius. So the absolute velocity that I will see if I am standing in a fixed frame is this vector, okay, which is perpendicular to the radius. Now, in order to decompose this vector, I need to know what is the angle it's doing with the horizontal direction. So I need to determine what is this angle here, okay? To do so, I can just do small mathematical analysis. If I look at my figure, this angle here is theta. And also, this angle here is theta. Okay, so this angle between if I consider the external angle, okay, here, this one, this external angle is equal to 2 theta. Okay, so I can deduce that the angle between the radius and the horizontal is equal to 2 theta. And since the velocity of point C is perpendicular to the radius, and the vertical line, yani y-axis if you want, is perpendicular to the horizontal, then I can say that the angle between VC and the vertical is 2 theta is 2 theta. Okay, so now what can I do is to divide VC into two components. One along here, if you remember, when we work in rotating axis, we will choose to decompose or in big I, big J, or in small I, small j. Okay, it's up to you. Here they choose to divide on big I, big J, and big I, big J are the conventional horizontal and vertical vectors. So this is big I, and this is big J. If you want to work in small I, small j, you can also. You can take small I along the rod and small j perpendicular to it. Try to do it if you want as practice, and you will see that you will get at the end the same result. Okay? So now, what we will do now, we will project VC in two components. It's negative along I, positive along j, and the angle with j is 2 theta. This is why, as you can see here, the velocity vector Vc can be written as Vc times minus sine 2 theta along I plus cosine 2 theta along j, and of course 0 along k because it's a 2D motion. Now, second step, I will move to V relative. We know that the color is translating with respect to the rod, so it's moving along AB. هلا هون كمان you can expect إنه إذا omega counterclockwise, the color will go downward. يعني حيكون along minus R. If you didn't pay attention, it's not a problem. When you solve, بيطلع لكم V relative negative. So you can put equal to plus V relative times, and you project V relative on I and J. As you can see, V relative is along the rod. يعني to project along I should multiply by cosine theta. So here they assumed إنه الcolor طالع لفوق, which is wrong. ساعتها بيطلع لهم V relative negative. So it's V relative times cosine theta along I plus sine theta along J. Now, plus omega vectorial AC. Concerning omega, omega is given, it's counterclockwise, so it's positive, and it has only a component along k, so it's plus 3k vectorial. مشان هيك إذا بتلاحظوا هون 0 0 because no component along I and j, and omega vectorial vector AC. How to obtain vector AC? AC also is can be decomposed into components along I and J. So to see it, let us look at the figure here. This is vector AC. I can decompose it along I. بس شوفوا شو أهين تشتغلوا بسمول I small j. إذا بتشتغلوا بسمول I small j, you only have to project one term اللي هو VC. والباقيين ال V relative وال AC, you don't have to project them because they are along small I. يعني in general, working along small I small j will facilitate your calculation. Okay, try to do it. احنا already عملناها أنا وياكم في a previous problem. Try to do it. You should obtain the same result, and it's much easier than what they did. So for AC, you can decompose it into two components. The first component is for this one, okay? You can decompose it into two parts, because as you can see here, this distance, if you take like this, okay? This distance from this point to this one is R, header radius R, okay? And this distance, you can calculate it because you know the angle. So this is the radius of the circle, and this is the projection. So this is R, and the angle here is 2 theta. So the projection of this distance on the horizontal is R cosine 2 theta. This is why in total, the projection of AC along the horizontal is R plus R cosine 2 theta. While the vertical projection here is just R sine 2 theta. So now, after writing all our vectors, all we have to do is to expand vectorially the relation and to compare along I and J. And what will be the two unknowns? VC magnitude and V relative. So by comparing along I and J, you can solve for VC and V relative. Okay. Now, we cannot stop here because they want to find the acceleration of point C, not just the velocity. But even if they didn't ask you for the velocity of C, you should pass by this step because you need V relative. Okay? You need V relative because you will use it in the Coriolis acceleration term. Okay? So always you should pass by this step before going to the acceleration relation, since the Coriolis acceleration involves V relative. So now let us go to the second step. Now we will relate the acceleration of C and A. So also we will go back to the acceleration relation in rotating axis, which is AC absolute equals to A relative vector plus, if you remember قلت لكم إنه this term you can simplify it by putting minus omega square times AC. It will give you the same result. Okay? And you have also plus here هن ما حطوا كل الترمز. I will put them for you. هن plus alpha vectorial AC. But here in our case, okay, alpha vectorial AC is 0. Why? Because the rod is rotating at constant velocity. يعني alpha is 0. وأكيد plus acceleration of point A, but كمان AA is 0 because it's fixed. So also this term cancel out. Plus the Coriolis acceleration. So this is the Coriolis acceleration اللي هي 2 omega vectorial V relative. So as I told you, you need to calculate V relative before starting this step. Okay? وإلا بتزيدوا بصير number of unknowns أكتر من بصير 3 instead of 2. So now let us see which term is equal to what. First, for AC, this is the absolute acceleration. And since C is rotating about a fixed axis, so if you look at C from the fixed frame, you will see that it's doing rotation. You know that in rotation about fixed axis, we can decompose the acceleration into two components. One that is tangent to the path and one that is normal to the path. So here, for AC absolute, I can write it as two components. AC tangential, which is perpendicular to the radius, and AC normal, which is directed towards the radius. Concerning AC tangential, we don't know what is the value of it. لأنه ما بنعرف what is alpha of C about the center. So we will keep it as unknown. هنسميها AC tangential, unknown in magnitude, but just we know its direction. Okay? هي مثل الvelocity. This is why, as you can see here, the unit vector تبعها هو ذاته. So it's AC tangential times minus sine 2 theta cosine 2 theta 0 مثل اليونت فيكتور تبع الفيلوسيتي. هلا اذا كانوا VC و AC tangential opposite ساعتها بتطلع لنا AC tangential negative. So we cannot know before doing the solution. Okay? Plus, so this is AC tangential vector. We should add to it AC normal. هلا concerning the normal acceleration, you can easily find it. Why? Because already you have calculated VC from the previous step. And you know that the normal acceleration of a point in rotation is VC square over R. So the radius of rotation here is equal to the radius of the circle. So this is the magnitude of ACN. The magnitude of ACN is known, but AC tangential is not known. So for the normal vector, since UN is downward, okay, like this, and we know that the angle here this angle between UN and the horizontal is 2 theta. So this angle is known to be 2 theta from the previous analysis. So we can just decompose into ij, and it has a negative, an has a negative I, negative j component. So it's minus cosine 2 theta along I, minus sine 2 theta along j, and 0. Equals to, from the other side, you have first, for A relative, also, you know that relative to the rod, the color is translating. So it's moving along AB. Okay? And they assumed A relative upward. You can know from the calculation if it is positive, then it's true A relative is upward. If it is negative, then A relative is down. So it's A relative times the same unit vector of V relative. It's along the rod. Okay? Now, plus or you do just minus omega square AC, or you do this vectorial product. So AC, we have already calculated vector AC from the previous step. We just have to replace. It is the same vector here. And we still have the Coriolis acceleration. So it's plus 2 omega of the rod, which is only along K. And since it's counterclockwise, it's plus omega K. Vectorial V relative. This vector was calculated already from the previous step here. So because we have calculated V relative from first step, we can just replace and get this term. So now we end up, when we write the acceleration relation, we will just have two unknowns. When we do the expansion and we compare along I and J, the two unknowns will be AC tangential and A relative. So by solving, you can get here your values. As predicted, V relative will be negative because it's clear that it's moving downward. And also A relative is negative. This means that your color is accelerated because V relative and A relative are of same size. And in this way, we have calculated the different unknowns for the position. And for theta, they asked for a certain particular value of theta. The value of theta is 45 degrees. So for this value of theta, you can solve, just replace theta by its value and solve for your unknowns. Any question on this problem? Please try to solve it again, but projecting on small I, small j. You will see that it will be easier for you to solve the system. Okay? One final problem. You will see now that the ideas will be repeated. The same concepts now, we will see them here. It's very similar to what we did in the previous problem. So you have block B of the mechanism is confined to move within the slot member CD. If AB is rotating at a constant rate omega AB, determine the angular velocity and angular acceleration of member CD at the instant shown. So here, again, same thing. To know which type of formula to use, I will look at my points and how they are moving. Point B is doing what? Point B is a fixed point on AB, so it's doing rotation about fixed axis. But at the same time, it has a relative motion with respect to bar CD, which is rotating. So since I have relative motion between B and CD, then when I want to correlate VB to VC, I will use the rotating axis formulation. Okay? And what I know here, I know completely the information about AB. I know that it's rotating at a constant rate and omega AB is given. So omega AB is 3 and alpha AB is 0. So I can find what is VB easily and what is AB. The absolute velocity and the absolute acceleration of B can be calculated because B is a part of the rigid body A. And once I calculate VB and AB, then I can relate to C because they are asking me to find what is the angular velocity and angular acceleration of CD. So I will use the relative motion of B with respect to the rotating rod in order to determine what is the angular velocity and what is the angular acceleration of the rod. Okay? So to start with, the first step is to find the velocity of B and the acceleration of B. I can use vectorial method, and I can use a much easier method, because whenever I have rotation about fixed axis, I can say directly that the velocity of B is perpendicular to AB. So since AB is horizontal, then the velocity of B will be vertical downward, since omega AB is clockwise. So I can write directly that VB vector is minus omega AB, which is 3, times A, the radius, which is 0.1, along J. So VB vector is minus 0.3 J. And once I find the absolute velocity of B, I can now use it, okay, to correlate with the rotating rod, CD. So now I will write the following. VB absolute is equal to VC, which is 0 because C is fixed, so this term will cancel out, plus V relative, which is the relative velocity of C with respect to the rod CD, plus omega of the rod, omega CD, vectorial CB. Now, for VB, they choose to use the vectorial formulation. So نحن استعملنا the easiest method لأنه it's rotation about fixed axis. You can also use the vectorial relation to get VB. إنه تقولوا إنه هي VA, which is 0, plus omega vectorial AB. So this is what they did here, هو omega vectorial AB. Omega AB, because it's clockwise, هي minus omega ABK. Vectorial AB اللي هو along I only, so it's AI. So you will get back to our result اللي هو minus 0.3 J. Now, for V relative, come in here, they are decomposing along big I, big J. We know that B is moving relative to CD. It's doing translation, and it's moving along CD. So it's doing with I an angle of theta. Here also they did a wrong assumption. اعتبروا انه V relative up. Okay, this is why when they do the calculation, لانه it's clear for us انه اذا AB عم تبرم لتحت, B will go downward. يعني اذا بتحطوا plus V relative هيطلع لكم V relative negative. So plus V relative sine theta along I, cosine theta along J, because we know that CD is doing an angle theta with the vertical. So this is the projection of V relative. Now, plus omega CD vectorial CB. هلا omega CD you can assume انه هي clockwise. اوكي لانه اذا بتعملوا شويه interpretation بما انه omega AB عم تعمل هيك والبي عم تنزل, it will rotate like this. So إذا ما قدرتوا كتير تقشعوها it's fine. Whatever is the assumption you do, فيكم تحطوها counter clockwise, but when you solve for it, okay, حيبين إنه هي positive. Sorry, إذا أنتوا حطيتوها counter clockwise حيطلع لكم negative result, يعني هي clockwise. So don't worry about the assumptions, because you can say after, you know, because I got a negative result, my assumption is wrong. So because they said here إنه هي clockwise, حطوها 0 0 minus omega CDK. Vectorial for vector CB. For vector CB, as you can see, this distance is given to be equal to B, and we project CB along big I, big J. So it's cosine theta along big I, big J, sorry, sine theta along big I. So it's B sine theta along I plus B cosine theta along J. So now, this is a vectorial relation that will give you two equations, one along I, one along J. And what will be your two unknowns to find V relative and omega CD? هلا انتم فيكم بس تجيبوا اوميجا سي دي، بس عادة بيكون coupled، يعني حيكونوا coupled equation, so you solve for two equations with two unknowns. هلا عادة بس ناخدهم small I small j. if you project on small I small j in general بيطلع الايكويشن يعني كل وحدة بتعطيكم وحدة من ال variables. So this is why I advise you in general to work in small I small j إلا إذا they specified for you to project on big I big j. Okay, so please try to do practice with these two problems and to project along small I small j and solve your system. You will have easier equations, but of course same result. So this is for velocity relation. Now we will proceed in a similar way for the acceleration relation. So as a first step, we will start by finding what is the acceleration of B. So B is doing rotation about a fixed axis. I can decompose it into tangential component, AB tangential. But remember إنه omega AB is constant. So alpha is 0, يعني ABT is 0. So you only have a normal component for acceleration of B, and it's given by A and B is along minus I, directed towards the center of rotation, and in magnitude it is equal to omega AB squared, which is given times R. Okay, R هون هو ال A. So as you can see here, هن حطوا الفورمولا الطويلة الفيكتوريال. If you do this expansion, you will get minus omega square times A along I. This is the absolute acceleration of B. Now, from the other side, you have, as usual, هيدا relation for rotating axis. For A relative مثل ال V relative هي along الرod لأنه it's translation. So as you can see here, it's the same unit vector of V relative. So this will give you the acceleration vector. And in case A relative you got is positive, يعني هي لفوق. And in case it's negative, يعني it's downward. Plus what? So this is A relative vector. Plus alpha CD اللي هي unknown. Okay, بس هن they assumed إنه هي clockwise. This is why حطوا minus alpha CD. Vectorial CB. وvector CB already جبناه من first step. So you just replace by this vector, it's the same here. B sine theta plus B cosine along I plus B cosine theta along J. Now, minus هيدا الترم هو minus omega square CD. This term is minus omega square CD. وomega CD, okay, جبناها من the previous step. So this is why always you should start by the vectorial relation of velocities to get V relative and omega CD, because you will use them bill acceleration relation. Okay, so it's minus omega square CD times vector CB. And finally, we have the Coriolis acceleration اللي هي plus 2 omega CD vectorial V relative. وأكيد هلا صرنا نعرفهم omega CD و V relative because of the previous step. Okay, so all we have to do is to replace the values we got for omega CD و V relative in the equation, and then by doing the expansion we will just have two unknowns here اللي هن A relative and alpha CD. So here also you will get two equations with two unknowns, which will allow you to solve for the relative acceleration of B with respect to the rotating rod and the angular acceleration of bar CD. Okay, and from the sign you will know if your assumption was right or not. If we check it here, as expected, V relative حتطلع negative because it's moving downward. And since B is accelerating, A relative is also negative, while for omega CD طلعت positive يعني مظبوط هي clockwise، بينما alpha CD طلعت negative يعني the rod is decelerating. وبليز انتبهوا على شغلة، مش ضروري إذا الcolor accelerating تكون الرod accelerating. يعني هيدي في منهم بيفكروا هن مغلطين. no it's possible انه البوكس يكون الcolor يكون accelerating while the rod is decelerating. okay, any question on this problem? So these are review problems for chapter 16. We are done يعني with all the material. In case you need anything, you have any problem while studying, you can just send me a message on Microsoft Teams. And if you feel we need to do extra practice, I'm ready whenever you want. Okay?
Thank you, Doctor. Doctor, quick question. We
Yes.
have chapters 15 and 16 for the finals or from 12?
Look, let me check with Dr. Rani, but I think 14, 15, 16.
Okay. Thank you so much.
Okay, welcome. Any other question? Okay, bye-bye.
Thank you, doctor. Have a nice day.
You too, bye-bye.